Number 21 is a finding from consensus diligence audit of Unstable protocol, where it was a major severity finding related to the timing category. In this case, it was the abuse of a sliding window where users could collect interest by only staking M tokens momentarily. For more context, when users deposited M assets in return for lending yield and swap fees, users received credit tokens at an exchange rate which was updated at every deposit. However, it enforced a minimum time frame of 30 minutes in which the interest rate would not be updated. A user who deposited shortly before the end of the time frame would receive credits at the stale interest rate and could immediately trigger an update of the rate and withdraw at the updated and more favorable rate after the 30-minute window. As a result, it would be possible for users to benefit from interest payouts by only staking M assets momentarily. The recommendation was to remove the 30 minutes window such that every deposit also updated the exchange rate between credits and tokens. This finding is therefore related to the timing issues discussed in number 143 and 177 of Security Pitfalls and Best Practices 201 module, where system design has to anticipate and prevent abuse of timing aspects and assumptions of the protocol. Number 22 is a finding from consensus diligence audit of Banker V2 protocol, where it was a critical severity finding related to the timing category. This issue was about Oracle updates that could be manipulated to arbitrage rate changes by sandwiching the Oracle update between two transactions. The attacker could send two transactions at the moment the Oracle update appeared in the mempool. The first transaction sent with a higher gas price than the Oracle update transaction so as to front run it would convert a very small amount to lock in the conversion weight so that the stale Oracle price would be used in the following transaction. The second transaction sent at a slightly lower gas price than the transaction that updated the Oracle so as to back run it and effectively sandwich it would perform a large conversion at the old stale weight, add a small amount of liquidity to trigger rebalancing, and then convert back at the new rate. The attacker could obtain liquidity for step 2 using a flash loan and use that to deplete the reserves of the pool. The recommendation was to not allow users to trade at a stale Oracle rate and trigger an Oracle update in the same transaction. This finding is related to the transaction order dependence aspect discussed in number 21 of Security Pitfalls and Best Practices 101 module, ordering aspect discussed in number 178, and freshness aspect discussed in number 185 of the Security Pitfalls and Best Practices 201 module. Number 23 is a finding from consensus diligence audit of Shell protocol, where it was a major severity finding related to the input validation category, where certain functions lacked input validation, such as uint should be larger than 0 when 0 is considered invalid, uint should be within constraints or thresholds, int should be positive in some cases, length of arrays should match if more than one related arrays are sent as arguments, and addresses should not be 0 addresses. The recommendation was to add input validation and incorporate tests that check if all parameters had indeed been validated. We've discussed the importance of input validation on function parameters and arguments in number 138 and 146 of Security Pitfalls and Best Practices 201 module. Number 24 is another finding from consensus diligence audit of Shell protocol, where it was a major severity finding related to access control. There were several functions that gave extreme powers to the protocol administrator, of which the most dangerous was the one granting capability where the administrator could intentionally or accidentally deploy malicious or faulty code that could drain the whole pool or lock up the users and LPs tokens. Also, the function safe approve allowed the administrator to move any of the user's tokens in the contract to any address, which could be used as a backdoor to completely drain the contract. The recommendation was to remove the safe approve function and improve users' trust by making the code static and unchangeable after deployment. We discussed the importance of least privilege principle in number 192 and principle of separation of privilege in number 193 of Security Pitfalls and Best Practices 201 module. This is also related to access control and trust issues we discussed in number 148, 149, 160 and 172 of Security Pitfalls and Best Practices 201 module. Number 25 is a finding from consensus diligence audit of Lien protocol, where it was a critical severity finding related to denial of service, where a reverting fallback function would lock up all payouts. In the context of the transfer ETH function, if any of the Ether recipients of such a batch transfer were to be a smart contract that reverted, then the entire payout would fail and be unrecoverable. The recommendation was to implement a pull withdrawal pattern or ignore a failed transfer, leaving the responsibility then up to the recipients. We have discussed denial of service in number 176 and concerns with Ether handling functions in number 158 of Security Pitfalls and Best Practices 201 module. We have discussed concerns with calls within loops leading to denial of service in number 43 of Security Pitfalls and Best Practices 101 module. We've also reviewed OpenZeppelin's pull payment library, which specifically addresses this pull versus push aspect of Ether transfers in number 158 of Solidity 201 module. '26 is a finding from consensus diligence audit of the LAO protocol, where it was a critical severity finding related to denial of service. The issue was related to safe rage quit and rage quit functions used for withdrawing funds from the LAO. The difference between them was that while rage quit function tried to withdraw all the allowed tokens, safe rage quit function only withdrew some subset of those tokens as defined by the user. The problem was that even though one could quit, they would lose the remaining tokens. The tokens were not completely lost, but they would belong to the LAO and could potentially still be transferred to the user who quit. However, that required a lot of trust, coordination, and time, and anyone could steal some of those tokens. The recommendation was to implement a pull pattern for token withdrawals. We've discussed denial of service in numbers 176 of Security Pitfalls and Best Practices 201 module. 27 is another finding from the consensus diligence audit of the LAO protocol, where it was another critical severity finding, again related to denial of service. The issue was that if someone submitted a proposal and transferred some amount of tribute tokens, these tokens were transferred back if the proposal was rejected, but if the proposal was not processed before the emergency processing, these tokens would not be transferred back to the proposal. Tokens were not completely lost but belonged to the LAO shareholders who may try to return that money back, but that required a lot of coordination and time, and everyone who rage quit during that time would take a part of those tokens with them. The recommendation again was to use a pull pattern for token transfers. This is again related to the denial of service aspect we discussed in number 176 of Security Pitfalls and Best Practices 201 module. 28 is another finding from consensus diligence audit of the LAO protocol, where it was another critical severity finding, again related to denial of service. The specific issue here was that emergency processing could be blocked. The rationale for emergency processing mechanism was that there was a chance that some token transfers may be blocked, and in such a scenario, emergency processing would help by not transferring tribute tokens back to the user and rejecting the proposal. The problem was that there was still a deposit transfer back to the sponsor, and that could potentially be blocked too. So if that were to happen, the proposal couldn't be processed and the allow would be blocked. The recommendation again was to use a pull pattern for token transfers, and this is again related to the denial of service aspect we discussed in number 176 of Security Pitfalls and Best Practices 201 module. Number 29 is another finding from Consensus Diligence Audit of the Lao Protocol, where it was a major severity finding, again related to denial of service. In this issue, token overflows might result in system halt or loss of funds because some functionality such as process proposal and cancel proposal would break due to safe math reverts. The overflows could happen because the supply of the token was artificially inflated. The recommendation was to allow overflows for broken or malicious tokens to prevent system halt or loss of funds, but recognizing that in case such overflows occur, the balance of tokens would be incorrect for all token holders in the system. This is again related to the denial of service aspect we discussed in number 176 of Security Pitfalls and Best Practices 201 module, and also the dangers of integer overflow underflow we discussed in number 19 of Security Pitfalls and Best Practices 101 module. Number 30 is another finding from Consensus Diligence Audit of the Lao Protocol, where it was another major severity finding, again related to denial of service. The issue was that while iterating over all whitelisted tokens, if the number of tokens was too large, a transaction could run out of gas and all funds would be blocked forever. The recommendation was to limit the number of whitelisted tokens or to add a function to remove tokens from the whitelist. This is related to the aspect of loop operations leading to denial of service from out of gas exception in number 42 and denial of service from block gas limit because of looping over arrays of unknown size we discussed in number 44 of Security Pitfalls and Best Practices 101 module. And the broader aspects of denial of service in number 176 and gas issues we discussed in number 182 of Security Pitfalls and Best Practices 201 module. Number 31 is another finding from Consensus Diligence Audit of the Lao Protocol, where it was another major severity finding, again related to denial of service. The issue was that the summoner could steal funds using the bailout functionality. The bailout function allowed anyone to transfer the kicked user's funds to the summoner if the user did not call safe rage quit. The intention was for the summoner to then transfer those funds to the kicked member afterwards, but the issue was that it required a lot of trust on the summoner for doing so and they could deny such a transfer. The recommendation again was to use a pull mechanism which would make the bailout function unnecessary. This denial of service aspect is something we discussed in number 176 of Security Pitfalls and Best Practices 201 module. Number 32 is another finding from Consensus Diligence Audit of the Lao Protocol, where it was another major severity finding related to timing and denial of service. If the proposal submission and sponsorship were done in two different transactions, it was possible to front run the sponsor proposal function by any member so that they could block the proposal thereafter. The recommendation of pull pattern for token transfers would solve the issue by making front running ineffective. This is related to the transaction order dependence aspect discussed in number 21 of Security Pitfalls and Best Practices 101 module and denial of service aspect that we discussed in number 176 of Security Pitfalls and Best Practices 201 module. Number 33 is another finding from the Consensus diligence audit of the Lao protocol, where it was another major severity finding related to timing and denial of service. Any member could front run another member's delegate key assignment, where if one tried to submit an address as their delegate key, someone else could try to assign that delegate address to themselves, making it possible to block some address from being a delegate forever. The recommendation was to make it possible to approve delegate key assignment or cancel the current delegation. Commit reveal methods could also be used to mitigate this attack. This is related to the transaction order dependence aspect discussed in number 21 of Security Pitfalls and Best Practices 101 module, and denial of service aspect that we discussed in number 176 of Security Pitfalls and Best Practices 201 module. An interesting point to note here is that the project decided to not fix this finding as reported in the audit report, presumably because they did not see this as a major severity issue in their risk model. As discussed in the module on Audit Techniques and Tools 101, the findings and recommendations reported by an audit team may not necessarily be fixed by the project team for different reasons, but usually because they are outside the threat model or within the trust model of the project. Number 34 is a finding from Trail of Bits audit of the origin dollar, where it was a high severity finding related to denial of service. The specific issue was that queued transactions could never be cancelled. The governor contract contained special functions to set it as the admin of the time lock, and only the admin could call time lock cancel transaction. But there were no functions in governor that called time lock cancel transaction, which made it impossible for time lock cancel transaction to ever be called. The recommendation was in the short term to add a function to the governor that calls time lock cancel transaction, and in the long term consider letting governor inherit from time lock, which would allow a lot of code to be removed and significantly lower the complexity of the two contracts. This is related to the denial of service aspect that we discussed in number 176 of Security Pitfalls and Best Practices 201 module. Number 35 is another finding from Trail of Bits audit of the origin dollar, where it was a high severity finding related to access control. Missing access controls in the time lock execute transaction function allowed proposal transactions to be executed separately, circumventing the governor execute function. The recommendation was to allow only the admin to call time lock execute transaction. This is related to access control aspects discussed in number 4 of Security Pitfalls and Best Practices 101 module, and also in number 141, 148, 149, 150 and 172 of Security Pitfalls and Best Practices 201 module. Number 36 is another finding from Trail of Bits audit of the origin dollar, where it was another high severity finding related to access control. The governor contract contained special functions to let the guardian queue a transaction to change the time lock admin. However, a regular proposal was also allowed to contain a set pending admin transaction to change the time lock admin, which posed an unnecessary risk in that an attacker could create a proposal to change the time lock admin itself. The recommendation was to add a check that prevented set pending admin to be included in a regular proposal. This is related to access control aspects discussed in number 148, 149 and 172, and also the principle of complete mediation discussed in number 196 of Security Pitfalls and Best Practices 201 module. Number 37 is another finding from Trail of Bits audit of the origin dollar, where it was a high severity finding related to reentrancy. Missing checks and no reentrancy prevention allowed untrusted contracts to be called from mint multiple function, which could be used by an attacker to drain the contracts. The recommendation was in the short term to add checks to cause mint multiple to revert if the amount was zero or the asset not supported, and also to add a reentrancy guard to the mint multiple, redeem and redeem all functions. And in the long term to make use of Slither and incorporate static analysis checks into the CI/CD pipeline, which would have flagged the reentrancy. Other recommendations were to add reentrancy guards to all non-view functions callable by anyone, ensure to always revert a transaction if an input is incorrect, and to disallow calling untrusted contracts. We have discussed these aspects in number 157 of Solidity 201 and number 13 of Security Pitfalls and Best Practices 101 modules. Number 38 is another finding from TaylorBit's audit of the origin dollar, where it was a high severity finding related to error handling. The issue was that several function calls did not check the return value, without which the code is error prone and may lead to unexpected results. The recommendation was to check the return value of all function calls that return a value. We have discussed this in number 74 of Security Pitfalls and Best Practices 101 module and number 142 of Security Pitfalls and Best Practices 201 module. Number 39 is another finding from TaylorBit's audit of the origin dollar, where it was a high severity finding related to denial of service. Several function calls were made in unbounded loops, which is error prone because it can trap the contracts due to gas limitations or failed transactions. The recommendation was to review all the loops to allow iteration over part of the loop or remove elements depending on gas consumption to prevent denial of service. This is related to the aspect of making external calls within loops leading to denial of service from out of gas exceptions, discussed in number 43 of Security Pitfalls and Best Practices 101 module, and broader aspects of denial of service in number 176 and gas issues we discussed in number 182 of Security Pitfalls and Best Practices 201 module. Number 40 is another finding from TaylorBit's audit of the origin dollar, where it was a high severity finding related to data validation. Under certain circumstances, the OUSD contract allowed users to transfer more tokens than they have in their balance, which is caused by a rounding issue. The recommendation was in the short term to make sure the balance is correctly checked before performing all the arithmetic operations, and in the long term to use the TaylorBit's tool Echidna to write properties on arithmetic invariants that ensure ERC20 transfers are transferring the expected amount. This is related to aspects of token handling in number 159, data validation issues in number 169, and numerical issues in number 170 we discussed in Security Pitfalls and Best Practices 201 module.